All right, good morning, everyone. So today we're going to be talking about soil electrical conductivity and how we can use that in precision ag, how that becomes an important layer, especially what are some of the main factors that we should be looking into when using that layer for precision ag applications. So we're going to start off with a quick lecture here. So if you go on the course website, I have posted a lecture under today's class on March 18th. If you click on that, it should launch that for you as well. And as you already know, if you want to download this as a PDF and take notes directly on it, you can do that. And if you want to follow that just on the screen or on your browser, you're also welcome to do that. All right, so again, today we're going to be talking about soil apparent electrical conductivity. This is a very popular layer in precision ag for different reasons, and we're going to cover some of those today. So today, my goal for this lecture and this exercise is going to be to discuss about apparent soil electrical conductivity and what it is, discuss how it is measured, and why that is an important layer for us in precision ag.
Hey, quick question.
Yes.
Do you remember what I was trying to remember like how to download it. Do you remember what the key sequence was? Because I remember there was like a control something command that you could do to download it.
Yeah, so on my side, if I push on my keyboard, if I push the letter E, it turns into like a continuous scroll slide deck. Once it does that, if you just go on your on your browser, for me would be under File, Export as PDF. On a Windows, I think it's probably going to be something similar, perhaps not exactly like that, but you want to go somewhere that you can export it. So on my side, if I do export as PDF, I can just export that and then take notes on a PDF. But the first step there would be to push on your keyboard to push the key for the letter E, and that makes it continuous, like a continuous scroll rather than like a slide deck. And then you on your browser again look for somewhere like File, Export as PDF. Were you able to find on your site?
I'm looking, but I'm not finding the PDF thing. I was able to get it to the continuous scroll, but
Let me see here. Neva, did you? Okay, so Neva here is saying that if you're using Windows, if you just push Control P, I think that's probably prompts you to print. And then when you
yep.
own there, you can probably like save as PDF. So maybe like on my side, I see like a PDF, save as PDF when I ask to print. On a Windows, I'm not sure. Neva, what do you, is that something you see, something similar? Okay, were you able to find that option on your side?
Yes, sir.
Okay, awesome. All right. Okay, so to begin with, what is electroconductivity? And we're going to be referring to that as EC. So this is just a measure of how much electrical current is conducted through a medium. And normally it's measured in Siemens or millisiemens per meter. So we're going to see a lot of these units here when you look at, especially at what we're going to be seeing as far as apparent electrical conductivity data for precision ag. So really, we're trying to assess here within a medium, it could be any type of medium, how much there is a source of electricity and there is that electricity interacts with that medium. We're trying to measure after that interaction, how much is left or how much is being conducted through the medium. That's really what electric conductivity is doing for us. And this is going to relate to the level of ionic charges able to conduct electrical current. So if you think about it, if you recall from your chemistry days, if you have pure water that has no ionic charges, it has no salts in it, it will not conduct electricity. So this really relies on having charges in that medium that can conduct this electricity, and then we measure at the end of that interaction how much is being conducted. And really the first use of this in agriculture in general was to measure salt concentration in soil water and relate it back to crop growing suitability. So this is especially so it was developed for conditions where you have saline or sodic soils, where you have so much salt concentration in that soil that it actually limits plant growth because it limits water uptake. So if you have a lot of if you have a lot of salts in a soil, your matrix potential is your osmotic potential of that soil is going to be very low, making it very difficult for plants to extract water from it. And so these soils here are problematic for agriculture because of that. And so it's important to identify if the level of salts in a soil are high enough to be classified as saline or sodic soils. And again, this goes back to being able to identify these areas in a field or even in multiple fields, and classify that as far as crop growing suitability. So if a soil has too many salts, too much of a salt concentration, crops will probably most likely not be able to be grown there, even if you add water, because those salts are holding on to that water so strongly that plants cannot take that up. So initially, this approach, this measurement was developed to diagnose those types of soil conditions. So the way that this traditionally was used is you would go to a field, collect a soil sample. So pull a whole bunch of soil samples, bring that to the lab, saturate that soil sample with water, and then the extractant, so that what you get out of that water interacting with that soil would be then measured for electric conductivity, which here we're calling ECE, between two electrodes. So imagine again, you go to the field, you pull up a whole bunch of soil samples, bring it to the lab, add water to it, and then that extractant, you test for electric conductivity using two electrodes. So this is still the golden standard of this type of measurement, and this is how it was developed initially. However, that is very time consuming and labor intensive and really not very feasible for precision ag applications if you think of it. I mean, if you have to go to a field and pull all these samples, I mean, we do that for some other nutrients, but in this case here, there are other ways that became more popular in precision ag when it comes to measuring electric conductivity. So that would be the electric conductivity you measure directly from the soil extractant, right? So that is our golden standard, our actual value that you measure electric conductivity based on. But then we have this term for bulk soil apparent electric conductivity. So in the word, I guess bulk is important here, and also the apparent electric conductivity is also important here. So what happens is, if you go to directly, so this would be sensors that we would take out to the field and measure the bulk electric conductivity of that soil. So what happens here on this diagram is we have the solid phase, which is, this color here, more kind of like spotted color. we have the liquid phase, which is the smooth color in gray, and then we have the air phase. So really, when we go to the field and we measure in situ apparent electrical conductivity, we're just emitting some sort of electrical magnetic field or electricity through the soil, and we're measuring how much is being conducted through that soil matrix, right? So really, that could be through three different pathways. So one would be, if you look at this first path, is really going through the solid and the liquid phases of the soil. That would be one way that you would conduct that electricity through soil. The other one is being completely just through the liquid phase, as you can see here on this second path. The third path would be completely just within the solid phase. So as you can see, if your solid phase is contiguous, you would also be conducting some electricity through that solid phase as well. So when we're measuring bulk soil apparent electrical conductivity, we're really not discriminating between these three phases. We're just getting the overall signal coming from them. And if you really think about it, when we do this in the soil, so the actual electrical conductivity that we just talked about in the previous slide, you would be really extracting the salts from the solid phase, but you're really only measuring that electric conductivity on the liquid phase of that extractants, right? And so this is one of the reasons why when we go and measure this in situ, it is on the bulk soil. So it's not just on the liquid phase, but it's the bulk of that soil matrix. And also because we call it apparent because it's not a direct measure of electric conductivity as it is when you do in the lab. It is apparent because it is related to that we could measure in the lab, but it's more general because, again, it is going through different phases and it's also going through the soil matrix rather than just the soil water extractant. So for us to measure this in situ, there are three main methods. The first one is electrical resistivity. The second one is electromagnetic induction. And the third one is time domain reflectometry, TDR. We're going to talk about each one of these three methods here in more detail. So the first one here being electrical resistivity. This is probably one of the most popular, at least that I've seen in precision ag applications. One example here would be the Varius 3100 model. So any of the various models, if you ever heard of like a Varius grid being used to collect data on soil apparent electrical conductivity, that's what it is doing. It is an electroresistivity approach. So the way that a Varius works is, so this is just a Varius rig. It is something that is pulled behind a tractor most of the time. It could be pulled behind an RTV as well. But the way that it works is that it has a set of discs here. So if you see here, there is a transmitting electrode, which is this one right here. So if we just focus on the set of the first three discs here, so the first disc or electrode is the one that is transmitting the electricity signal. And then we have just on this left half here of the rig, we have one receiving electrode right here and another one right there. So the difference here is that the one in the middle is the one emitting the signal. And then depending on how far the receiving electrodes are from the emitting one, you're going to be basically collecting that resistivity and relating that to conductivity data that will encompass or comprise different soil depths. So the closer the receiving electrode is from the transmitting electrode, the shallower soil depth that is being integrated on that signal. So normally what we would see when you look at various data is going to give you two depths. It's going to give you a shallow depth, soil apparent electrical conductivity at a shallow depth and at a deep depth. The difference there is just these two receiving electrodes are at different distances from the emitting electrode. So again, the one where the receiving electrode is closest to the emitting electrode would give you a signal of shallow depth because it is integrating at a shallower soil depth after leaving the transmitting electrode until it makes its way to the receiving electrode. On the other hand, the receiving electrode on the far left here, so the farther away from the transmitting electrode, would be integrating the soil signal at a deeper depth as it leaves the transmitting electrode, make its way through the soil and reaches the receiving electrode that's farther away. So just to recap that again, the receiving electrode closest to the transmitting electrode is going to be associated with soil electric conductivity at a shallow depth. And the receiving electrode farther away from the transmitting electrode is going to be integrating the signal at a deeper depth. Because of that, we get the signal for two soil depths, and we also have that same setup here on the right side. So one thing here that happens that is one of the differences between this approach and others is that even think of this view as kind of like you're right behind this various rig and you're looking at it from behind. These here may look like, I don't know, maybe a needle or something like that, but these are actual discs, right? So these discs are cutting through the soil, emitting and receiving this electrical signal as it cuts through the soil, right? So it's actually in contact with the soil, cutting the soil and emitting that signal, and then reading that on the receiving electrodes, relating that to electroconductivity in this case. So that would be the electrical resistivity approach, and that's how it works in the field. The second, let me see if I can. All right. The second method here is electromagnetic induction. This is also a popular, perhaps is the second most popular one in precision ag applications. So one commercial example of this is a product from Geonix. I'm just giving you one model here that's EM38. There are different models. There's also another commercial example called Dual-M or Duo-EM. I'm not sure how they pronounce that, but it sounds like Duo-EM. It's another example of induction, and it works a little bit differently from the resistivity option. So what happens here is, again, think that you are looking through this. It's just like a cross section of that equipment where you have two coils here. You have a transmitting coil and a receiving coil. So the transmitting coil will emit an electromagnetic signal that creates these eddy spirals in the soil that are then read by the receiving coil. One difference here, one of the main differences between this and the previous method is that the electromagnetic induction does not have to touch the soil. It has to be close to the soil, but it does not have to touch it. It does not cut through the soil as the previous example here. So it's just creating that electromagnetic field interacting with the soil, and then the signal that arises from that is being read by the receiving coil. Another one of the differences between these two methods is that the electromagnetic induction method pretty much has its depth of measurement fixed because you have these coils already set up. They're not really movable within this equipment. And this is also something that would be pulled by a tractor, an RTV, maybe another type of equipment, but it has to be moved through the field. There are some examples of the initial works of this where people would actually carry this. So it would be just like a setup, kind of imagine like a long pipe that a person would kind of like wear as a necklace sort of, and then just hold that on the field and walk with it. It's not very precision ag oriented in that way, at least. But this way here, it would be because both the various example I gave earlier and this one I'm showing you here on this commercial example of Geonix, they both are taking these measurements and are integrating that with GPS. So you know exactly what part of the field you are when you are taking these measurements as you move along a field. So that's mostly the reason why these have become easier to collect this type of data. You don't have to go to a field and collect soil samples anymore. and also because it's integrated with GPS. So we know the location of the signal as it is moving through the field. And another difference here is that because on the electromagnetic induction setup, you have this equipment that it has basically set depths, right? So it's not really easy to change the depths that you are trying to integrate that signal, as perhaps it would be with the previous example, because you just have a rig and you can move those disks around a little bit. And so we could change the depth that you're integrating over with the previous example, but not so much with the electromagnetic induction example here. All right, so the last of the three methods here is called time domain reflectometry. This is something that this is just a picture from a paper, so it doesn't look really sharp or really new, but it is one of the methods that it's been used. Here, what we're seeing is just this equipment mounted on a tractor. So it basically has two metal rods that are inserted into the soil. Again, we have one of the rods emitting that signal, that electromagnetic signal, and the other rod just receiving that and relating that to soil electric conductivity. In any case, so this is something I've used for research purposes before, where you just have like a handheld TDR equipment that you just go to a part of the field, you insert. It also has these two rods, maybe not as deep as the ones we're seeing here, but it also has these two rods that you just push into the soil, take a measurement. Potentially that equipment also has a GPS with it, so it takes a measurement and a position, and then you just keep moving to the field. In this case specifically here, it is the least scalable of the three in situ methods, mostly because you do have to stop, insert into the soil, take a reading, remove it from the soil, go to your next spot. So TDR of the three we're talking about is the least scalable because you do have to stop to take a measurement, whereas the first two examples of electroresistivity and electromagnetic induction, you do not have to stop. You basically just drag that equipment as you're moving through the field, and it's just taking the measurements and the locations as you move. So this would be the least scalable of all three because you do have to stop to take a measurement. All right, and again, I guess just to recap again, so all these three methods here that we're doing in situ on the field, they are measuring for us the apparent soil electrical conductivity. And that is what we're going to be using here. It's not the actual electric conductivity, which is something you only get when you take a soil sample, bring to the lab, do wet chemistry with it, and so on. Okay, I do want to take a very important moment here to talk about what affects soil apparent electrical conductivity. This is something that is going to be important for you as you plan your studies or your, actual on-farm application of this. And even though a lot of times we cannot really change things as much and really plan to the best of our capacity just because of conditions, it's still important for us to keep in mind what affects the reading that you get out of a Varis or any of these other equipment, and just keep that in the back of your head as you look at data. So as we would, hopefully have already gathered this information up until this point of the lecture, is that the main thing that impacts soil electric conductivity is soil salinity, right? Again, this measurement overall was developed to test soil salinity levels. In our case, in Precision Ag, that is rarely the reason why we use it, right? So we use this for different reasons, most of the time, not to really relate to soil salinity. It is going to be impacted by soil water content, and we're going to see how that is. And this is something that we need to keep in the back of our heads when we're planning for collecting this type of data. The third point here is soil texture, and this really is the reason why we use in Precision Ag. So if you have not seen this type of data before, soil electric conductivity is going to, what we hope to do is actually to have everything else constant and only allow soil texture to be impacting the reading you get out of soil electroconductivity. That is our main goal in precision ag. But also other things here like soil temperature, soil organic matter content, and soil bulk density and porosity. So all these things and some others will be impacting the reading that you get out of a soil electroconductivity equipment that is measuring that apparent signal on the soil, on the bulk soil. And something very important here is that because soil ECA, and I guess maybe I have not made this clear, but the A here is for apparent. So soil electroconductivity apparent is impacted by so many different factors. The data that you collect from this can only be used in relative terms to that field. We really don't take these values here to compare different fields, different years, different fields. It's not really a measure that you can say, well, this field here has overall higher and this one has overall lower. It's more about within this field, I have areas of high and low because you have so many factors impacting the reading that you get that it should really only be interpreted with the data of that sampling approach you took in the field. All right, so let's try to understand how are some of these variables here impacting apparent electroconductivity, beginning with soil salinity. So what we have here is, let me just walk you through this plot and we're going to talk about it in more detail. So we have apparent electroconductivity here on the x-axis and the actual extracted electroconductivity. So the one that you would get in the lab when you pull a sample from the soil, bring to the lab, add the water to it, and then measure on the extractants what is the electroconductivity. So what we see here is first, as your actual electroconductivity, so the one you're getting from the lab, which is on the y-axis here, as that is increasing, your bulk soil conductivity is also increasing, right? So this is the relationship that we really drive, that we want to see is that, as the actual truly measure in the lab conductivity increases, your apparent also increases. And if you think about it here, so these different lines are 3 different soils where we have different soils with different texture levels. And so we can see that this relationship here between what we are assessing with an in situ equipment and what we would get in the lab is different depending on those soils, right? So overall, as the soil actual salinity increases, your apparent salinity also, or apparent electroconductivity also increases, and that relationship depends on the soil type, mostly because of texture. So just again, for us to keep in mind, these values should be thought of in relative terms about that field only, but not really to compare different fields because this is one of the reasons for that. All right, so soil water content also impacts it. Let's look at a plot here. So just walking through, on the x-axis, we have volumetric water content. On the y-axis, this symbol is a little bit different from the previous plot, but this actually just means apparent electroconductivity. So what we see here is that as you increase volumetric water content on the x-axis, you're also increasing apparent electroconductivity on the y-axis. And that is modulated by soil salinity, which on this plot here is being depicted as the sigma W is soil salinity. So we see that as soil salinity increases, the extent of the change of apparent electroconductivity also increases as volumetric water increases. So there's a lot of things going on in this plot, but really the overall, or I guess, interaction between what we're actually measuring, which is on the y-axis here, apparent electroconductivity, how that is being impacted by as your soil gets wetter, you get a stronger electroconductivity, which I guess it would make sense, right? You have more of that liquid phase to interface with the solid phase and get a stronger signal. And also that signal increases in strength as you have more salts in that soil. I guess that, hopefully that makes sense to you as well. And this is something that we need to keep in mind. So if you think about it, on the previous example, we were talking about that as soil salinity increases or salt levels in the soil increase, you increase also your electroconductivity. There's really not much we can do about soil salt levels or any concentration of nutrients that would be considered salts here in the soil. We really cannot change that. However, water is something that we have either more control over if it is an irrigated field, or at least we have more knowledge about it if you know that you're going and taking a measurement of soil EC, apparent EC, right before a rain, right after a rain. I guess you wouldn't go right after a rain necessarily because maybe you wouldn't be able to get into that field. But just for us to keep in mind here that something that you would not want to do is, for example, I don't know, if you have an irrigated field and you, for some reason, decide to irrigate part of that field only, and not the other part of it, and then you come with a various rig to collect soil EC data. We do not want that to happen because then you're adding this extra factor here, that is soil water content, and you're going to have a different signal where you have a wetter soil compared to where you have a drier soil. So we do not want to have water as being the main driver of soil ECA. We want that to be texture, right? Again, in precision ag, we want to relate soil electroconductivity with soil texture and not with any of the other factors that could impact it. So now let's talk about soil texture and how that impacts ECA. So as you would imagine here, the more electric charges you have in the soil, the more potential you have for that soil to be conducting electricity. Because of that, sandier soils that have a lower cation exchange capacity, so it has a lower number of sites that have charges to be interacting with nutrients and or water. In that case, you have a lower conductivity from a sandy soil, which again has a lower cation exchange capacity overall. You have an intermediate conductivity from silty soil, and then really the soil texture that would conduct more electricity and therefore have a higher soil ECA would be a clay soil. Right, so this here, what we're seeing in the screen is really the reason why we use soil ECA in precision ag purposes, because we need to plan well to make sure that the signal you get is mostly controlled by texture, right? That's what we want it to happen. And in that case, then we can use these maps to relate that data to actual textural classes in your field. Now, why is this important in precision ag? So when soil apparent electroconductivity is mostly controlled by texture, it can be used to create texture-based zones. And the reason why that is important is because we can most of the time relate different textures in the field with yield limiting factors, like, for example, water and nutrient availability and cation exchange capacity. So it would be, we do relate these conditions to different yield limiting factors. So for example, you would assume that a sandier soil, which in this case would have a lower soil electroconductivity, would be a very well-drained soil. However, it would have a lower capacity to hold on to both nutrients and water. And if you think of the flip side of that, on a soil that is more clay, perhaps that would have a higher potential to hold on to both nutrients and water. And in the case of water, it could, if it is too much, if it has too much clay, it could actually be on the bad side of that, right? It could cause waterlogged conditions. So we're really trying to relate here this soil ECA signal with texture, as that would be one of the most important layers that we can use to understand how yield is being impacted in that field. So here's just one example from one paper where, in this case here, so on the left side here, we have a soil EC map. And on the right side, we have yield map from that same field. So what we can see here is, at least for this condition here, low electric conductivity that is being shown on that north side of the field is being, I guess, correlated with low yield in this field, whereas high EC on the south side of that field is being correlated with high yield in this case, right? So probably there's something related to texture here, where the low EC is maybe a sandier spot of that field, where, you know, maybe the plants ran out of water because water drains more quickly through a sandier soil, and it has less nutrients, or the capacity to hold on to nutrients is decreasing a sandier soil. And maybe the high EC here would be the opposite. Maybe it's a little bit either more siltier or clear soil, where you do have more charges that can hold on to nutrients and potentially also retain more water in this field. So that is relating back to high yield. All right, I do have a quick quiz here for you. And what I want to ask you is the following. So I have 3 questions for you. You can answer these questions and send them to my email. So my question for you is, overall, is lower or higher apparent electric conductivity better for crop yield? So based on what we talked about here in this lecture, based on the concepts we just went through, I wanted to know your thoughts on this. And then I wanted to tell me why you think that's the case. So if you tell me, well, lower soil ECA is better for crop yield because of this, right? I want you to tell me why. And then I want to challenge you and ask you to think of and describe a case where it may be the opposite relationship as what you answered first. So let's say that on the first question here, you tell me that higher ECA is better for crop yield. Then you're going to tell me why you think that is. And then I wanted to think about a case where lower would be better. So the opposite, whatever you answer on the first one, I want you on the third one, I want you to tell me the opposite of what you answered on the first one, in a case where the opposite would be better rather than what you answered on the first one. So I'm going to give you here 5 minutes for you to answer this. Send your answers to my email. Let me set a timer as well. Just get this out of the way. If you have any questions or any clarification, feel free to ask. We have the last 30 seconds here. If you want to wrap up your answer and email me. All right, we are out of time. Make sure you send me your answers. I'm still waiting for a few of you. All right, I think we got everyone in here. So I was able to look at the first ones that submitted your answer, and I just want to, walk you through what we see normally here. And some of the examples that I read from your answers were really good as well. So overall, we do relate higher ECA better with crop yield, right? That's normally what we see most of the time. Again, going back to higher ECA being related to soils with more cation exchange capacity, also potentially related to better water holding capacity as well. Mostly because lower ECA could be, sandier soils that have lower water holding capacity, lower nutrient holding capacity as well. So overall, the higher the better. And the why, we just talked about it. However, that doesn't have to be always the case. And you're going to see, especially here in Georgia, where that's not always the case. So one reason that it may not be the case, and I saw some people saying this in their answer, is to begin with, this method was initially intended to measure salts, right? So if you run your soil ECA equipment and you get a high ECA reading, it could be because you have saline or sodic spots in the field that have way too many salts and therefore high ECA. And that is not a good thing that we want to have, because those spots will be probably spots that plants going to have a harder time growing because of that water limitation. The salts hold on to water very strongly. Plants cannot access that water, and therefore it's almost like they're under drought, even though that may not be the case when you look at rainfall and irrigation amounts. So first off, it could be related to saline or sodic soils, higher salt concentrations, right? So that would be one of the cases where this is not, higher is not better. Another case here, which I think is perhaps one of the most common ones that we're going to see in Georgia, is if you have a very heavy clay on the soil surface. So if you do, I don't know if you all have seen this in grower fields or even on your own backyards, if you have a backyard that you can grow like a garden or something. So in my home, I have a backyard that grass has a very hard time being established and growing and developing, because my surface soil layer of my backyard is a very hard clay type of soil that that plants just have a hard time to set roots and just to develop there. It's also to the point where even though it has a lot of clay, but it is at a slight slope, which means that water because water infiltrates more slowly. If it is at a slope, which is something we see also a lot here in Georgia, that water is just going to run off instead of trying to infiltrate in that soil. So it has a harder time just for water to even infiltrate, it just runs off, right? So those would be cases where you may have high ECA, and that may be a bad thing in your case, because first, it could be high salts. Second, it could be just a very hard soil pan that plants have a hard time establishing in those areas, and even just breaking through after planting through that soil. So sometimes those spots have also lower germination, lower emergence rates, which is one of the key steps when we're growing a crop, is that the crop actually emerges and you have plants there. So if you don't have as many plants as you intended, that may also be impacting your final yield. All right, so we were gonna move to our exercise next, but it's already 10. So what I'm gonna ask you all to do is, let me take your attendance on GitHub. And I do want to mention, well, let me first open the issue for that. So clean your attendance there, and I do want to tell you that I have already uploaded the partial script and the data for the soil EC exercise. We're only going to work that on Friday, because this Wednesday it is our exam. As you all know, it's going to be in person in your on-campus, in-person location. However, I do ask you to get ready for the class on Friday by already doing a git pull or just downloading the GitHub repo. And so there's going to be a new data set there called Soil EC. There's going to be a new partial script for Soil EC as well. So I do want to ask you to bring those files into your computer and already set up our next just folder structure in our studio project. I want to show you on my side what I have. So what I want to ask you is to create a 09 Soil EC folder at the main level of the course folder on your side. So 09 Soil EC. Inside of that, you create code data output. You move the code into the code folder, the data into the data folder, and then create a RStudio project. And then next Friday, we'll start right off the bat without having to do this in class. All right, that's all I had for today. Anyone has any questions about either today's content or about the exam coming up on Wednesday?
I'd say Clint and Tipton, I spoke with Skylar this morning and he said something about like me retaking the exam like Thursday at 1.
Yes. Would that work for you, Clint?
Yes, sir.
Okay, awesome. Yeah, sounds great. All right, any other questions or? Well, I guess if not, then we're wrapped up for today. I will be posting all of your grades and feedback by today, just so you know. And then I'll see you all on Wednesday, except for Clint. But everyone else, I'm expecting in class on Wednesday for the exam. And just to clarify as well, last class I said that this lecture would not be in your exam. It will actually be. So make sure you go through the slides here and understand what we talked about today, as we're going to have a couple questions related to this on the exam on Wednesday. All right, that's all I had. Thanks, everyone. See you on Wednesday.